we have a shorter lecture today because there is a activity for you all, and I will describe. You'll be getting an email in 30 minutes. Okay, so homework is due Friday. The office hours are listed right here. Anya had office hours this morning. Christian has office hours at 1. John has office hours 6 to 10. Tomorrow, office hours is 1 p.m. Patricia, 3 p.m. Gabe, and then Friday, 8 and 10. Okay, so take advantage of those things. And so we've been talking lots about graphing and transformations, and today is going to be the last day we talk about graphing in the XY plane. Old-fashioned, graphing, the type of graphing you really need to master for your SAT test. Tomorrow, we're going to cover some more advanced topics like graphing in the polar plane, which is very, very useful, and I think you all will find it very interesting. We'll also cover three-dimensional graphing and possibly four-dimensional graphing, and we'll discuss what it's like to graph space versus time. So tomorrow will be very enriching, but less useful for the SAT. So far we've discussed the following things. We've discussed the transformation rules, which I wrote in green yesterday, and I hope many of you wrote that down because I think yesterday I did a better job explaining them, and those rules were written more clearly than the day before. And we've done many examples. Yesterday we ran, 20 or 30 examples. And so today we're going to see a few more examples, and we're going to incorporate a few new ideas, but it's mainly just going to be a quick review before you have to sort of fly on your own, okay? And that's the goal, right, for you to be able to do these on your own. And that's exactly this last point, that you'll be tasked with this assignment. Check your email at 10:30. So at various stages, usually in this course has previously been a in-person course, and we used to meet, and some of you I know were participating in that course last year and the year before because I was there in person helping. And we've always done group pictures. This year we are going to have to do a group screenshot. So I think at the end, towards the end of the lecture today, maybe around 11:30, we'll do that. Okay, so on to the math. Suppose we have some function f of x, and I've drawn some arbitrary curve here. This is just an example. This curve is kind of inspired by the polynomial, a cubic polynomial x cubed, but this is just a shape. And the reason I don't want to work with an actual algebraic thing, the reason I want to give you just sort of a curve is because I want you to be thinking about these transformations geometrically. So don't think of this as anything algebraic, just think of it as a shape, okay? And it's a function, and it's given by f of x. We're going to discuss various transformations just using this shape. So this is the most general discussion of transformations because we're going to simply describe what the shape looks like without thinking about numbers and points and stuff, okay? So what would f of x plus 3 look like? And this is going to be very participatory. Let's see, the first name I saw was Soliana. Soliana, what do you think f of x, if this is f of x, what would f of x plus 3 look like?
It would be translated up 3.
It would translate it up 3, very good. And so it would look like so. And this is 3 units. Great. Okay. What would 1/4 of f of x look like? And I'm going to call on, okay, let's see, Monica. Nothing for Monica. Maria. I'm trying to call on people I haven't heard from. Isaac, I haven't heard from you in a while. Daniel? No one. Okay, Daniel, go ahead. What would 1/4 of f of x look like if this black line is f of x?
Can you repeat the question again?
Yeah, so it's written right here. What will 1/4 of f of x look like if this black line is f of x? What would this 1/4 do? So this is f of x.
It would make a curve in the slope.
Say that again, say it louder.
It would make a curve in the slope.
It would make a curve in the slope. Well, okay. I'm not
Like
sure
this
what
is
you
the
mean by
first. This is the first time of me seeing this. So
Okay, so you haven't. Oh, that's right. You were absent. Okay.
yeah,
Okay. So basically, okay. So I think I emailed you actually the video, the
yeah.
lecture videos. So okay. So I'll let you go today. Okay, because you haven't seen this before. Let's see. Does anyone else know? Can anyone else help Daniel? What kind of? First of all, is this a vertical or horizontal
It's
transformation?
a vertical. It's a vertical compression if you just want to say that.
It is a vertical compression. How do you know it's a compression?
Because like it's not. I guess the easiest way to say it is like it's not inside the parentheses where the horizontal would go.
Okay. Well, what if I had 4 times f of x? Is that a vertical? It's outside the parentheses. Is it a vertical?
Yeah, so that's a vertical stretch now.
So what's the distinguishing factor between?
Oh, so a vertical stretch is anything above 1, and a vertical compression is anything below it.
Right, so we have this rule that if you have some factor alpha and it's multiplying your function, if alpha is greater than 1, that's a stretch, and if alpha is less than 1, that's a squeeze. And so this 1/4 is less than 1, so this is a vertical squeeze, and so this function will get squeezed vertically. See how it's been squished in the vertical direction. It's like you're pushing it together, okay? So this is what 1/4 f of x looks like. Great, let's move on. Someone else, please tell me, what would 1/2 f of x plus 1 look like? So this is combining 2 things. Let's see, do I have to call on people or are people gonna participate? Let's see, Mauricio, go ahead. Or Adi, go ahead.
It would be up 1 and a half compression, half squeeze.
Sure, and so everything you said was fine, but I would caution you, I would urge you to first do the transformations closest to
Okay.
whoever that was.
Closest to x first. All right.
Closest, I mean, you would get the same result in this case, but generally, and this is
Mhm.
actually a huge thing in physics and math, generally transformations are not commutative. And I can tell you why. Okay, let's do this first and then I'll tell you why later. So 1/2, so it's gonna be, that's a compression vertically because this number is less than 1, just like the 1/4 in the last example. So that's going to be like this, see? And then the entire thing gets moved up 1 unit. Okay, this wasn't very good, but I think you get the point, right? The entire red line is just moved up here. Sorry, that's not a good drawing, but this is 1 unit. And so it's squished and it's moved up. Okay, so why are transformations not commutative? Well, it's very easy to see. This is an aside, okay, aside. More for the juniors and seniors. But generally, in physics, well, and in any type of math, generally
It's just like algebra. Like if one step messes up, then you can't do the entire thing again. Like if you had like a reflection and you did the up 1 first, it wouldn't work.
No, it actually would. If you had a reflection and then you moved it up 1.
If you had a reflection and then if you had a reflection but you stretched it first, it would work.
A reflection, if you took like the absolute value of something before. So there generally you have to work from inside to out, and the actual reason is that transformations can be written as matrices. So you can rotate things, you can translate things using matrices, and you know that matrices, if I have 2 matrices A and B, that the product of 2, so if this is transformation 1 and that's transformation 2, this does not equal, you know that we talked about matrix multiplication in the first week of the course, and we know that matrices don't commute. So this is really the more mathematical reason. It's because all of these transformations actually correspond to matrix multiplication, okay? And we're not going to get into this as much, but
that makes sense. If it's matrices, then it makes sense because it's like all those numbers you have to put in.
Yeah, so generally matrices don't commute, and you can test it with some matrices if you want to see that matrices don't commute. But anyway, in many algebraic cases, like these basic things, they do commute, but I would caution you. Okay, so do go from inside closest to x to farthest from x. Should be the progression. Okay, someone else. Thanks, Adi. That was very good. What would if this is f of x, this black line, what is f of x minus 6? Let's see. I'm going to call on someone else. Let's see, Mauricio. I had called on you, but I didn't hear from you. Or anyone. Okay, so Mauricio said, good, shifted to the right. And Adi said 6. Yes, so together you gave me the right answer. So this is, first of all, a horizontal transformation because it's inside the parentheses, right? It's affecting the x. And you know that the horizontal transformations sort of appear to go as the opposite as the vertical transformation. So -6 means shifting to the positive x direction by 6 units. So this thing is going to get moved over. Wasn't perfectly well done, but this is 6 units. And what if it were f of x plus 6? Then which way would it go? Obviously, it would go to the other direction, right? Left 6 units. But be very careful with this, with the minus sign and plus sign inside the argument. Remember that there's this apparent contradiction that I sort of have belabored it. It's not really a contradiction. It's something you have to get your mind around. That this is you have the opposite behavior because of the way we write transformations, because everything is written in terms of x. Right? Y is on one side of the equation, x is on the other. So it appears that x is being treated differently than y, but that's not true. Okay, so does this make sense? I hope this is, so people miss this on the quiz, like left and right. So I hope this is very clear now. Okay, someone else. What would 2 times f of x minus 3 look like? So first of all, what do we have? What is this minus 3 doing? Moving it to the right, just as the last one. And what is this 2 doing?
Stretching it.
Stretching it which way? Vertically or horizontally?
Vertical.
Right, because the 2 is outside of this f of x. And so moving it to the right 3 units, we would have something like this. And then stretching it vertically, well, that's just going to pull it up. Oops, okay. Not quite that much. But it just makes it a bit longer. Okay, so sorry about my drawing. There should not be a curve here. Anyway, I think you will. Oh, gosh. Okay. Okay, you get the point, right?
You get the point, yeah.
It's something like that. Great. So we're slowly building these things up. We're slowly making them more sophisticated. Now we have 3 transformations. So what's the first step when you see something like this? What do you want to do first?
Take things that are inside, like closer to the x.
Mm-hmm. And what is that?
The 1. It'll move to the left.
Moves it to the left.
The compression.
The compression, right? So okay, so first you have this. And then this 1/3 squeezes the graph. Makes it look like that. And then what does the minus 3 do?
Just sit down.
It moves this blue line down 3 units. So you can see that I'm not labeling anything. I might just draw this arrow. I might write 3. But I'm not really labeling. I'm not caring about the points. I'm caring about the shape. We're caring about these transformations. So the green line is the final answer. Great. Does this make sense? We're slowly making these more and more sophisticated. Okay. How about the absolute? So thanks, Adi, for participating. I really appreciate it. I'm going to call on someone I haven't heard from. Ascension, I have not heard from you. Birka, I have not heard from you. Brianna, I have not heard from you. Fiona, Isaac, Caleb, Kennedy, Ria, I have not heard from you in a while. Robin, so any of you, what does the absolute value?
The bottom half of the graph will be like flipped to the top.
The bottom half of the graph will be flipped to the top. Very good. So the absolute value is sort of its own type of transformation. And you know that from definition of absolute value that absolute value turns negative numbers into positive numbers. And here indeed, look at the negative y, right? These are all the negative y values. The absolute value is just going to flip them. So now you have to be very careful with how you do it because it's easy to draw the wrong thing. You have to think very geometrically. How would this look? So I'm going to try to sort of copy exactly what's going on. And I think it will look like this. But there will be a sharp point here, okay? So the absolute value turns, so some of you will have learned about odd versus even functions. The absolute value turns an odd function into an even function when it's written this way. So there will be a sharp point here. So it looks kind of like a parabola, but it's actually quite different from a parabola because there is this, if you touch this, you'd say, ouch, right? It's sharp. Okay, does this make sense, what the absolute value bar did?
I have a question.
Go ahead, Adi. I think I saw it in the chat. Isn't the absolute value function like a v? So generally, the absolute value function is not a v. What you're thinking of is this function. This is the parent. This is the linear version. So this is actually the absolute value of a cube. If the black line was y, is x cubed, then this new thing is absolute value of x cubed. So
the difference is that like both the y and the x are inside the absolute value now. Because like it's f of x.
Yeah. So yeah, if you want to think about it that way, sure.
Yeah.
Well, that's not even the difference from this line. This is just a different function. You're taking a different function.
Yeah.
A different function.
Yeah. Absolute value is different from the actual parent function.
I guess so. Yeah, I think I'm understanding what you're saying, but
like the parent function's absolute value like works differently than the one that I'm like the one that's currently happening.
Yeah. So this is actually not the parent function of this problem. So the parent function, the absolute value doesn't really have a parent function. I think I might have misspoken a few days ago when I said like parent function of absolute value.
That was the v.
Yeah. So the absolute. So the okay. So this thing
is the v. Yeah.
Mm-hmm.
So.
Anyway, you can take the absolute value of anything, right?
Bye.
Okay.
Yeah, basically.
Great. Okay, that's a good question though. Yeah, the parent function really doesn't have. Sorry, absolute value doesn't truly have a parent function. Okay. Now we're really putting things together. So what's my first step? Anyone?
You just take whatever's close to the x.
Mm-hmm. And what is that?
The left 3.
Mm-hmm. So it's plus 3, which means I move left 3. Okay, that was awful. And now what do I do? What's next?
The absolute value would shift the graph.
It doesn't. The absolute value never shifts.
I mean, it makes everything negative go positive.
Right. So that's exactly this thing we just saw. And so this part goes away.
And the stretch.
Right. So now we have this 2 sharp point. Right. And now what does this minus 1 do? Yep. It moves it down 1. So it's the same graph, just moved down 1. So sorry, my lines are shaky, but you can see that this blue graph is the final answer. Make sense? So this is sort of what the homework is like. You have to go inside to out, and this is truly an example where if you did it backwards, you would not get the same graph. So if you went outside to in, you would have moved this down, and then you would have stretched that by 2, and then taken the absolute value, which would have given you a totally different graph, and then moved left 3, which would have been yet different. So absolute value is usually the thing where things that screws up the sort of commutation of transformations. It often, in your case, it will. Okay, so work inside to out. Okay, suppose this is an example that was similar to one we did yesterday. Suppose f of x looks like this. So it's sort of like a log function, but it also has this little dip in there, which is not usually seen in log functions. Okay, so this is our new f of x. What does the absolute value of f of x look like? And I think I redrew it here. What does the absolute value of f of x look like here? Well, I'm going to do the same thing. I'm going to make
just everything that's negative is positive, so let's go the other way.
Yeah, so all this negative stuff down here gets reflected across the x-axis, and there's a sharp point here again. and my new graph is this blue line. Yeah? So
Yep.
sharp point. Okay, now I have a question for you. What does f of the absolute value of x look like? So this was absolute value of f of x. What is f of the absolute value of x? How is this different from the absolute value of f of x?
Reflected to the other side.
Very good. How did you know that? Can you explain to everyone?
Well, if the other one f of x and f plus absolute value would be reflected across the x-axis, the absolute value of f of x would be reflected over the y value.
Yes.
So the y is like on the outside this time, so like the y-axis wouldn't change as much as it would. Only the like f of x, only the x would get like the absolute value sign. The y wouldn't change.
Yes, if I'm understanding you correctly, you're saying that nothing about the range of this graph is going to change. So the y values are not going to change.
Only
But the
domains.
x values will. And specifically, if you think about, if I think about something simpler, I really struggled with this, so I want to take time on this. Say I had the point -2, 1, and I took the absolute value of, here I'm taking the absolute value of x, right? And so if I take the absolute value of x, the point -2, 1 upon this
We'll go
transformation.
2, 1.
But yeah, I have to take the absolute value of -2, 1. And you can see that maps, that's just 2, 1, and that maps to the other side of the grid. So clearly for negative values, taking the absolute value of the x of the domain, which is like this case, gets from you get a reflection across the y-axis. But from this side as well, say I had the point, 1, 2 or something. Okay, so different example. Say I had the point 1, 2. And to apply the absolute value bars to that. So applying the absolute value bars, you can notice I would get this, right? But if there is sort of indeterminacy here, because I could also have -1. Absolute value of -1 is also 1. So this case would also work. If you're putting the absolute value bars, it's true that if I put absolute value bars on -1, I'll get the same point. And so
Do you want the point for it to be different? If we're using the different absolute value, you could do like 1, negative any y, and it wouldn't change.
that's true. Yeah, exactly. So I'm just using a point for this example, but yes. So my main point here is that the absolute value bars, when they're around the domain, reflects the entire graph across the y-axis. Whereas when the absolute value bars are around the function or the range, they reflect the negative parts, to the positive across the x-axis. So this graph
Wouldn't actually change.
Yeah, so this graph is actually entirely, let's see.
On the positive x side. So
This side is, this graph is entirely on the positive x-axis. However, Adi, actually, you remember yesterday we graphed the natural log of x. Remember in the grapher?
yeah.
And then we also graphed this, and we got this.
Oh,
So you can see that if I put one of these values in for x,
yeah.
I end up taking the absolute value bar, I get back to this value. So the main point is that the negative x-axis, the points on the negative x-axis, when taking the absolute value bars, give you the points, the old points, right?
Yeah.
And therefore taking the absolute value bars on the x-axis gives you a transform, flips the entire graph this way.
Well, not flips. It just makes another one.
Yeah, exactly. So the new graph is is this blue line. Thanks, Adi. Yeah, you're right. So taking the absolute value bars of this old black line gives you the black line itself that becomes part of the new graph, as well as its mirror image. Okay? So does that distinction make sense? Let's see. Okay, great. And if you want to see examples, you can always go to like Desmos or any online graphing program, and you can plug in your own things. It's a lot of fun, okay? But for the activity that you're about to start in 4 minutes, it's about to be sent out. Don't use Desmos. Use your knowledge, okay? And it'll be pretty obvious to me who's using their knowledge and who's using Desmos, because there's stuff that the calculator will know, so to speak, that you will not know, and that I would not know. So my point, yeah. So use your knowledge of transformations. But does this last example of absolute value make sense? Because I really struggled with this when I was in high school. So if I had, let's just do one more example. If I had, this will be good. Suppose f of x is given by the following. Let's see here. Say it looks like something like that. Okay. And now I'm going to ask you, what would this look like? So here's my function f of x. I'm taking the absolute value bars of both the domain and range. So what do you do first?
That's the same thing as the one before.
Well, it's not the same thing as the one before, because now
like the one like 2 times before, because that would, even if there's 2 absolute value bars, the one on the outside would still like change it by itself.
It would be all in quadrant 1.
It will be all in quadrant 1.
Yeah.
Okay, so
Well, no, that's not, because negatives turn into positives.
okay, so this is a great question, I think. So I'm actually going to sit on this for a bit because I don't want to confuse people, but I also want you all to think about what would just draw a general sketch, but think about it can be anything. Draw your favorite line, and think about what is the absolute value of f of the absolute value of x. Would it all be in quadrant 1? Would there be bits in quadrant 2? But we're going to. I can definitely tell you that there will be nothing down here. There will be nothing left in quadrants 3 and 4. Yeah.
It's like, yeah, it'll only be in 1 and 2.
Right, because we know that the big absolute values outside, they're going to take whatever's negative and make them positive. But think about this. Okay, so the quiz is about to come out. Not the quiz, sorry, the activity. And read the instructions on this activity. You're going to have 30 minutes to do it. There are 15 problems. So the ideal pace would be 2 minutes per problem. And then once you're done at 11 a.m., just in 30 minutes, scan and send the assignment to me. Okay, and you have my email, but it's also just, you can respond to the email that got sent out to you. Okay, let's see. I had like scheduled this thing to send, but why wait for it? Here we go.
There's no quiz today?
That's right, there is no quiz today. Okay. And I just sent it. So check your email. And it should be there. So I'll stick around here if people have questions, but enjoy.
I only got the one where it says only today's lecture.
Say that again. I couldn't quite hear you. You only got.
I only got the one where it says today's lecture.
Okay. So you haven't received the in-class assignment yet. Okay, let me troubleshoot here. I can also, I can send this. Okay, so you're on Zoom right now, right? So what I'll do is I'll just send it through Zoom. I think that's actually easier. Let's see. Okay, so I can send it through this chat. So if you haven't gotten the email, here it comes. Okay. So check the chat, and it's right there. So Long said, when it says include X or Y intercepts, does it mean to label the exact values? Okay, that's a good question. On the homework, I'm expecting you all to. But on this worksheet, if you miss a few, try to do it where you can. But if you miss a few, it's okay. I'm really looking for the shape more than the X or Y intercepts. I trust that you people can plug in numbers and shift things.
We still have to write the X and Y intercepts.
I encourage you to, because I think it helps solidify sort of the transformations. But if you don't want to, I'm not going to make you. Again, like it's less important than the goal of this activity, which is to. Yeah. So do it where it's easy to do. If it's going to be a pain, I mean, I wrote this worksheet, but at the same time, I don't want to impose needless things onto people. So. Yeah, use your judgment, but do put at least like 1 point on the graph. Every graph should have one easy point. If the X or Y intercepts are not easy, then go for maybe the vertex of the graph if it has a vertex, or some other point. So we have a sense of scale. Yeah. And once you're done with this activity, you're free to leave. And I'll see you tomorrow. But I'm going to stick around on this chat for a while here. So.